Hi guys, welcome. My name is Venkatesh Gowda and I am studying computer science at Sri Venkateshwara College of Engineering. So in today's video, we shall discuss about Boolean logic and combinational logic functionalities on a memory star based universal logic circuit. So let's start the video. So the title goes like this. Realization of a complete Boolean logic circuit and combinational logic circuit functionalities on a memory star based universal logic circuit. So these are the agendas that will be included in this video. So let's discuss one by one. So now let's get into the abstract part. MEMRISTORs are a promising solution for building an advanced computing system due to their excellent characteristics, including small energy consumption, high integration density, fast write-read speed, great endurance, and so on. In this work, we firstly designed three basic logic circuits such as XNOR 1, XNOR 2, and XOR gates by virtue of MEMRISTOR ratioed logic, and further construct 1-bit numerical comparators, 2-bit numerical comparators, and full adder 1 based on the above XNOR 1, XNOR 2, and XOR gates. Furthermore, we propose and design a universal logic circuit that can realize four different kinds of logic functions such as AND, OR, XOR, and XNOR at the same time. Subsequently, a full adder 2 is built using XOR function of this universal logic circuit. Compared with the traditional CMOS circuits, the universal logic circuit designed in this work exhibits several merits such as a fewer components, lesser power, and lower delay. This work demonstrates that memristor can be used as a potential solution for building a novel computing architecture. Now let's get into the introduction part. Since the invention of the transistor, it has been widely used in the various electronic devices. With the appearance of integrated circuits, the volume and power consumption of traditional circuits are greatly reduced, which promotes the rapid development of the field of microelectronics, and the size of transistors is gradually reduced to a nanometer level. This allows hundreds of millions of transistors to be integrated into a chip of unit area. Gordon Moore came up with the idea, what is known as Moore's law, which predicts that the number of transistors on the chips doubles every 18 months. This kind of computing architecture requires frequent data transfer between the computing units and storage units, which seriously affects the power consumption and the speed of the system. In order to address such challenges, many strategies have been proposed in the post-Moore era, including optimizing the preparation process of device circuits or exploring a novel logical computing architecture. Now we shall look at the literature review. First is the memristor basics. A memristor is a passive electronic component that relates electric charge and magnetic flux linkage, essentially acting like a memory resistor, where the resistance depends on the accumulated charge passing through it. The ability to store electric state makes memristors promising for building logical circuits without the need for additional transistors. Second is the universal logic gates. Several studies have shown how to construct universal logic gates like NAND or NOR using a combination of memristors, enabling the implementation of any Boolean logic function by cascading these gates. This is crucial for building complex logic circuits with memristors. So the benefits of memristor-based logic are it has high density, lower power consumption, and non-volatility. Second is the challenges and limitation. The challenges and limitation on this basic logic gates are device variability. The inherent variability in memristor characteristics can pose challenges for reliable logic design. Second is the non-ideal behavior. Real-world memristors exhibit non-ideal behaviors like leakage current and non-linear resistance switching, which need to be carefully considered. At last is the integration with CMOS. Integrating memristors with existing CMOS technology is a complex task that requires further development. Now we shall get to know about the design principles of the MRL. The concept of MRL was proposed by in 2012 arising from the nonlinear property of the memristor that is similar to the transistor operated in the triode region. One of the standout features of MRL logic lies in its ability to achieve AND or OR operation with just two components, leading to a substantial reduction in the overall device counts compared to traditional CMOS logic gates, especially for simple logic operations. Consequently, when tasked with the design of complex combinational logic circuits, The advantages of reduced device count become increasingly evident, directly resulting in a reduction in circuit area. Now we shall discuss about the logic gate modeling strategies. In 2008, at HP Laboratories designed and fabricated a memory device based on PT TiO2 PT sandwich stack structure. The conduction mechanism of PT TiO2 or PT devices can be explained by the motion of TiO2 or TiO2X interface caused by oxygen vacancy migration under external electric field. Under the action of voltage excitation, the thickness of TiO2 and TiO2X changes, that is proportion in the functional layer changes. The mathematical expression goes like this, where W of T is the thickness of TiO2X film, RON is equivalent to the resistance of the dope layer, ROFF is the equivalent to the resistance of undoped layer, and D is the total thickness of the film. Since the MEMRISTOR is a nano device, when a small voltage is applied into the MEMRISTOR externally, a large electric field will be generated in the resistance switching layer, resulting in the nonlinear movement of the storage ions. So the logic circuit goes like this. Now we shall discuss about the result. Compared with the XNOR or XOR gates proposed in the previous literatures, as forementioned, logic gates XNOR 1, XNOR 2, and XOR design in this work use fewer memristors and transistors. As shown in Table 1 and Table 2, in addition, we conducted power and area consumption calculations for XNOR 1 and XNOR 2 and XOR gates. For the result simulations performed in the Virtuoso, calculating power consumption for transistor or resistors is a straightforward process. This involved exporting transition power waveform data directly from cadence and subsequently computing the average power using the average function. However, the retrieval of power of waveform data for modeling memristors proves to be less straightforward. In these instances, we calculated the average power consumption for each memristor by determining the voltage difference across its terminals and multiplying it by the transition current flowing through the memristors. As per the formula, average then we summed up the power consumption for each module. As a result, the power consumption values are as follows. Now we shall get in the conclusion part. In conclusion, we leverage the computation principles of MRL to harness the unique advantages offered by the memristors as fundamental computation logic elements, and thus three basic logic gates XNOR 1 and XNOR 2 and XOR are firstly designed. Subsequently, some combinational logic circuits such as 1-bit numerical comparators, 2-bit numerical comparators, and full adder 1 are then constructed based on XNOR 1, XNOR 2, and XOR gates. Additionally, we proposed design a universal logic circuit that can realize four different kinds of logic functions such as AND, OR, XOR, and XOR. At the same time, moreover, a full adder 2 has been built using the XOR function of the universal logic circuit. The logic functions of all the circuits designed above were further verified using the cadence simulation software. Compared with the traditional CMOS counterparts, the logic circuits designed in this paper utilize fewer devices and exhibit lower power consumption and lower delay, making them promising candidates for higher performance artificial intelligence computing system. Particularly in the realm of the associative memory, this system offers significantly potential for improving task-related pattern recognition, information retrieval, and cognitive computing. So I hope the video was informative. Thank you.